Welcome to the Bytecode. I'm your host Shafu, and today's episode is about how to make Ethereum more secure, which is what the guys at Phylax are trying to do. To walk us through it, we have Odysseus. Thanks, Odysseus, for taking the time, man.
Thank you, man, for having me. It's a pleasure to speak.
Of course, of course. Yeah, Phylax, super interesting. Obviously, hacks in DeFi or in crypto in general are a huge issue, and you are trying to solve it. So, yeah, maybe walk us through it from a high level. What is Phylax trying to achieve?
Yeah, so we I started the company because I think that crypto can only win if we solve security, right? Is one of the biggest impediments in the adoption of crypto is actually security. You can't put all your livelihood in a smart contract because you fear that you will lose everything. And that's true even for the small folk like us, but even for institutions, right? And I deeply believe that we will win when the pension fund of Teachers Association in Canada will deposit 200 million in MakerDAO instead of Goldman Sachs. And to do that, we have to reduce the 1% chance of them, losing all their money, and we have to put it into 0.00 with many zeros, 1%. And this way we're doing Phylax. And to do that, we have to,
Yeah.
I think differently. And this is how we ended up in our first product, which is very different from, I think, anything that exists out there.
So, yeah, I totally agree. The likelihood of losing everything in a DeFi protocol is just way too high right now. So solving that is obviously would be a huge thing. Let's try to understand your approach from a high level. So, okay, so let's say we have this DeFi protocol
Mm-hmm.
that could be hacked, right? How how are you guys trying to prevent that?
Yeah, so it started from a very simple question, which is what if not all transactions need to finalize, right? I think what I found is that all of the hack prevention solutions or services that exist, they sort of depend on the hacker botching the execution, which is true in a lot of the attacks, right? The hackers are very good at finding vulnerabilities, but a lot of times they don't execute in a very sophisticated way, right? Which makes a lot of these other solutions useful, actually, and they are useful. But the problem is that the moment it's a cat and mouse game, right? And the moment all these solutions become very used, it will just force the hackers to become more, to execute more in a more sophisticated way. It's like antibiotics and bacteria, right? Where you use a lot of antibiotics and then you just force the bacteria to evolve to a strain that is that will not be killed by the antibiotics. So I believe we need a different paradigm. I think the only way for a hack prevention system to truly not be bypassable, to truly not depend on the hacker botching the execution, is a paradigm where the base layer itself somehow prevents the hack, right? So I started with that, notion of how can we incentivize the base layer, the nodes that create the network. How do we incentivize them to stop a hack, right? To stop a malicious transaction from landing on chain, landing and finalizing on chain. And to do that, you need to do two things. One thing is you need to be able to define what is a malicious transaction. what is a hack? How do you define that in a programmatic way, in an objective way? Because so far hacks are entities of the social layer. A hack is not something you can identify, on chain. It's something that people from the DApp or security researchers will say it was hacked. Because what is a hack? A hack is something where the business logic and the protocol logic diverge, right? So you force the smart contracts to do something which is protocol compliant. It follows the rules of the EVM and the Ethereum network, but it's not the intended behavior of the smart contracts, right? It's the business logic doesn't work as the creator intended to. So the first thing is to define what is a hack, and then after you define it, then you have to create a way, a mechanism to incentivize the base layer itself to not allow any transaction that belongs to that definition to actually finalize on chain, right? And after you do that, then you open a lot of questions around what happened, how you also stop, the full nodes to misbehave, right? To not allow only the bad transactions, let's say, and allow the good ones, right? So you need these two things. And this is what the credible layer, our first product, does. These are the two first primitives we're building: how to define a hack, and then how to incentivize the base layer to not allow it. And with this, the interesting thing that we found is that if you have these base primitives, if you have this on-chain definition of what is a hack, then you can actually build a lot of products. So we started building the hack prevention product. That was the first thing that came to mind, the first use case. But as I was abstracting away the concepts, you can actually build a lot of products. For example, you can build an insurance product, on-chain insurance, that doesn't depend on social consensus or an oracle or whatever. You can build bug bounties, which don't depend on a middleman to make sure that the DApp pays, etc. So once you have this on-chain definition of a vulnerability or a hack, the design space opens up immensely, and you can create this sort of ecosystem of products, which all of them contribute to improving security in the system, in the network, one way or another.
Okay, very interesting. I think what I found really interesting is the point of moving the definition of a hack from the social layer to executable code. I think that's a big one, right? So let's talk about how we can do that. So you have assertion system, right? How does the assertion system work?
Yeah, so the assertions is actually, I contributed to Foundry early in my protocol career a bit, and I really liked the DevX. And the assertions started as a way as a question as an answer actually to the question, what if you have a Foundry fork test on chain, right? What if you have that? And assertions essentially are off-chain computation, which you prove on chain. So it's a way for the DApp to define some state in a way, define whether some state is valid or invalid in a way that is more wide. That's what you can do on the EVM itself on chain, because this computation, this definition is evaluated off chain, right? So the user can define a wide range of conditions and essentially define what is a hack in a more complete way. And then while the evaluation will happen off chain, then you can evaluate whether that condition holds true or not. via proof system on chain. So it's almost as a, it's very similar to the whole concept of coprocessors, I would say, of coprocessors, where you do some off-chain computation and you evaluate the result on-chain with a very specific use case in mind, which is that of security.
Okay. So basically you have your contract change state, and after that you have some assertions that you execute to make sure that specific invariants aren't broken, right? So
Yeah,
how do
like
you
intent.
who pay?
It's like an inverse intent or a security intent, right? So with intent, you say what you want to happen on chain. This is you express what's the result you want on chain. So with the assertion, you express what you don't want to happen on chain.
Okay, so I define what I don't want to see happening. What can I access exactly from the on-chain state? And can I go back in the past? Can I get like an average over a specific number of blocks? What can I do exactly?
Yeah, so for starters, we have a very constrained syntax. So you can access the state before a state transition, like before the transaction which we are evaluating. So you can access the state before, you can access the state after, you can access the transaction object logs emitted during the state transition, etc. And you can access any state of the net chain at these points. But there is no reason to have this constraint, right? So we actually plan to increase how many historical blocks you can access. And also we're experimenting with embedding Oracle feeds, so you can also, which is very useful for Oracle manipulation use cases. And another use case we want to explore is cross-chain assertions, right? So you have a computation about the state, not about the state of only one network, but about the state of many networks. So this is very useful for bridges and cross-chain dApps, where, for example, a very simple assertion for a bridge is that for every withdraw you have on one chain, you want to have the deposit on the other chain, right? And all of the hacks against bridges break that invariant, break that assertion. Somehow the user, the attacker, manages to withdraw funds without having the relevant deposits on the other side, right? So somehow they manage to cheat the bridge and make it think there is a deposit on the other side, but in reality there isn't. But the interesting thing is, because it's off-chain evaluation, there is the design space is unlimited, right? So you can encode a lot of more things. And also because this is off-chain, you can also add them and remove them without changing the underlying smart contract. And this is a very important, I think, feature that we found, is that you get this on-chain expression, if you will, like the power of on-chain code, but with the agility of a Web2 SaaS product, where you can add and remove monitors or conditions and rules on the fly. If you want to make, for example, if you want to add a new condition on your smart contract, you have to redeploy, you have to upgrade, you have to re-audit. It's a very lengthy process. You don't have this agility. But they say that smart contract development is very like aerospace development. You can do a lot of work, but once the airplane is on the air, it's not easy to change the engine as it flies. But with assertions, because you associate these off-chain computations with the on-chain contract, you can change these off-chain computations without affecting the on-chain contract. So there is it's very useful because dApp developers, they can create assertions and they can continue adding assertions as they see their dApp being used and they find new emergent behaviors, and they further feel the need that they need to constrain or assert some conditions which they didn't think before, without having to go through lengthy audits or very expensive audits as well, right?
So are you guys writing like a custom EVM or something to enforce these new constraints, or how does this work?
Yeah. So
Okay.
I think this diagram will be very useful. So in reality, yeah, we have our own EVM called Phylax EVM, where so there is no need to have our own EVM, right? Assertions could be any language, evaluated in any way, but we made the decision to use an EVM as the evaluation engine and write assertions in bytecode, in EVM bytecode, and use cheat codes, specific precompiles to offer this extra functionality of switching between networks. And the reason we did that is for DevX, because in this way we don't force the developers to learn a new paradigm, to learn new patterns, right? To understand our own syntax. That the moment they stop using Phylax, it will become useless as a context to have. So by using bytecode as the language to express assertions, we enable them to not have to context switch. They can reduce the mental models they have. The use of cheat codes is very similar to Foundry. So they have all this context and all this knowledge they have, and they can just transfer it to use our product. And the moment they want to stop using our product, the mental models they have are still useful because it's Solidity or Viper, and it's cheat codes, right? So that was a very, I think, strategic decision for us. And the way it works is that basically, you have the transaction and some state, and is evaluated by the EVM to decide if the transaction is valid or not. But then the resulting state and the transaction and the original state also goes through the Phylax EVM, where it will evaluate whether it will basically say, okay, the transaction touched some states, touched some contracts, right? Of the contracts it interacts with, these contracts change their state. So we have to see if these contracts have associated assertions. And if they have these associated assertions, then we have to evaluate whether the assertions hold valid. And if they hold valid, then the transaction is valid and is allowed to continue through the transaction supply chain. And these assertions are defined by the contracts themselves. So we don't have any assertions, and we don't do anything on our own. We respect the sovereignty of the dApp. So if a transaction interacts with my contract, then it's my assertions that will be evaluated.
So basically, to write assertions, it's your normal Solidity, Viper, any language that compiles to EVM bytecode. What's special about the environment is that there are special cheat codes that I can use to access state I couldn't access on chain. The question I have is, how do you make sure that the correct person can deploy the assertions for their contract? Do you have do you need to prove ownership of the keys that deployed the contract, or how do you do that?
So that's a very
Okay.
interesting, philosophical and engineering problem. Philosophically is who should be responsible for deploying a contract, for writing assertions for a contract. For example, Seaport. It's a neutral, not upgradable protocol. Who should OpenSea should be able to write assertions for it. Who is the entity that should be, if there is an entity? I mean, when I say entity, maybe the right answer is that nobody can write assertions for Seaport. And then the second question, which is engineering, is okay, how do you prove that this entity that should be able to write assertions, how do you prove that on chain? So right now, the way we define this default ownership is either the deployer code, so the deployer private key, if they used the deploy bytecode, not deploy 2 or 3, and then is the private key and the public, the address of the owner interface. So if there is an owner interface to the contract, which is a well-established admin functionality as well, that person should be able to register the contract in our protocol to start writing assertions. And then we can also, obviously, we could also have our own magic interface that people can adopt to signal that this address should be able to write assertions. But for us, it's very important to lower the activation energy for people. We want to make it easy. And if we require dApps to implement a special interface, even if it's simple, I don't think that's a very good DevX. So we're starting with basically these 3 ways to prove that you are the entity that you should write assertions. But it's very possible that we will add more definitions in the future.
Interesting. Well, it's important, right? Because otherwise you could very easily DDoS the protocol, right? Make it unusable.
Yeah, of course.
Put in an assertion 3 equals false, and you can never use it again. Okay, interesting. Who's paying for the execution of the assertions?
So in our current first analysis of the mechanism, the entity that will pay for the execution of assertions is the dApp. So the dApp needs to have the dApp will pay the security fees to the assertion enforcer, as we say, to the entity that is responsible for executing these assertions to verify whether a transaction should interact with a contract or not. But there is actually quite complicated mechanism design in there and various attack vectors, grifting vectors that we're looking into. So there is a very high probability that we may change that. Clean way to do it from a mechanism point of view is for the end user to pay, similar as gas, right? So that you pay gas to send a transaction, and you also pay some security fees for the assertion execution that is related to the transaction. But that has a lot of very nasty UX externalities of because we want to make it's very easy. If we launch our network, right, we can just add the different gas or whatever, but we want to build a protocol that you can slide in on top of any existing network or protocol, right? That has been a very core design choice, because we want to go where the liquidity is, right? Nobody cares if we have our own most secure rollup. Users want to be on their specific networks for a number of reasons. And also, if we go to a network and we say, yeah, we have all these value propositions, but you have to change fundamental things about how the protocol works. That also it's not a good idea. So the complexity there is how we can externalize that to the end user, but in a way that doesn't make the UX suck.
Okay.
So this is part of active research.
Talking about executing assertions, did you guys think about maybe if you have like 100 assertions that you control it by, okay, I only need to run this assertion if a specific state got changed, so you don't need to run all assertions every time?
Yeah. So by default, we don't execute all assertions. every time. Now, this is part of the assertion enforcer code, right? So by default, it will only execute the assertions for the contracts the transaction writes to. So, if a transaction reads from a contract, we don't care. We don't need to run assertions of that contract. But we've added the concept of triggers, so you can specify whether an assertion should execute on Ether balance chains or storage chains. But we're also have scoped the more fine trigger. So, an assertion execute maybe on a specific function call or whether on a specific, storage slot change, etc. Right. So this is all part of the DevX as, an evolving concept as more and more people use assertions and we get feedback. And obviously it will affect the fee structure, right? So the more detailed triggers you have for your assertions, that means they execute more rarely. So they execute specifically when you want them to execute, which means that you pay less, right? But maybe at this point it's useful to talk about the two markets that this protocol, the product has. I think that's useful. So essentially, we start with the hack prevention use case. But as we were researching, it was obvious that there is two primitives here. So the core primitive is what we call the state oracle. And the state oracle is this primitive where the assertion adopters, as we say, the smart contracts that use assertions, they register. And then they submit assertions for the contracts. And they can, and it's either them or actually, you can embed into the protocol a way for them to delegate the assertion writing to what we call the assertion submitters. So this also opens the possibility of a market for auditors, security researchers to submit assertions to dApps. And this state oracle is responsible for storing the assertions and the registered dApps, and also responsible for evaluating the proofs. So we have two proofs. We have the proof of realization, which means that the on-chain state at some point resulted to an assertion being invalidated. An assertion the state of the chain, if you execute the assertion against the current state of the chain or some historical state of the chain with some boundaries, the assertion is invalidated, right? So basically this is the proof that the dApp was hacked, essentially. If you say the assertion invalidation is the definition of a hack, the proof of realization means the dApp was hacked. And then we have the proof of possibility, which is the proof that an assertion can be invalidated, right? So it's a proof where it says, I have a transaction, which if I send to the network, it will result to the invalidation of an assertion. And this can be useful for proofs of essentially, vulnerability. I have a transaction. I know a way to break your assertion. I haven't sent it yet. It's not live, but I know a way. So we have this primitive, the state oracle. And on top of this primitive, we can build products. We can build different dApps. And, the first dApp is the hack prevention, the assertion enforcement dApp. And why that's a different primitive is because the assertion adopters then go to the assertion enforcement market and they say, I want to enforce my assertions. So I have defined them. And now what I want is I want someone that I trust and who has transaction inclusion rights. I want them to enforce my assertions. For example, the sequencer of the rollup, right? So they go and say, you know what? I want to enforce my assertions. I want you to make sure that no transaction lands on chain that will invalidate my assertions. And I will pay you fees for doing so. And then if a transaction lands on chain, anyone can prove, a malicious transaction lands on chain, anyone can prove that the DApp entered into a state where an assertion is invalidated by submitting a proof of realization. And this will result to the sequencer, for example, being slashed, right? Because they didn't do their job. And this is how the state oracle is the primitive, and then the credible layer, the assertion enforcement, is a product, a DApp, that builds on that primitive, that uses that primitive to offer, hack prevention. But also then there is another DApp, for example, which is the bug bounties DApp, right? And that offers the ability for people to be, to being paid through bounties for submitting proof of possibilities. So if a proof of possibility is submitted for some assertion and I have a bounty associated, I will get some money. And, that person will get some money. And using the same primitives, you can build insurance. You can build, automated on-chain mitigation, for example, escape hatches. So if a proof of possibility is submitted, I want to automatically unwind my positions. And with account abstraction, this is possible without needing to delegate trust or, allow anyone to have control over your positions. You can submit a user op that says that is executable only if a proof of possibility is submitted, right? So this is how we have this primitive, the state oracle, and the assertions and the proofs as the baseline, and then we build all these products on top of it, which obviously the most exciting product and the first product we're building is the assertion enforcement, the hack prevention.
Nice. It's huge for bug bounties, right? This is like it's a proof now. There's no social layer
Exactly.
anymore.
No debate needed. No debate whether something is in scope or it's not in scope or whatever. And this is because probably there will be no KYC requirements. It's an on-chain primitive.
Mm.
In this way, there is actually an incentive to convince black hats to turn into white hats because you have found a vulnerability. There is no need for you to try to, if there is assertion enforcement, you can't hack the protocol. The assertion will be enforced. So why try that and not instead submit the proof and get the bug bounty and no KYC, you don't have to show who you are, etc., and you get a certain, you get the bounty, no questions asked. And also you contributed to the security of the DApp because now they know the vulnerability and they can, perform whatever mitigations they need to fix it.
Yeah. Did you think about would you need to audit your assertions, for example? Like it's an important piece of code, right? You would still have super hacks that not only hack the protocol but hack the assertions as well, right? That's still like a possibility.
Yeah, but assertions. So that's an interesting thing, actually. Assertions are security intents, right? So assertions they don't encode the how, they encode the what. So it's a much simpler piece of code because it doesn't perform the computation of how something can happen. It just makes an assertion on what's the end state. So it's a much simpler piece of code. You just say, I don't want this and this and this to happen. I don't care how that happened. So I think it will be probably maybe audited. But I think the most likely scenario is that dApps we will either have an on-chain market or an off-chain market where dApps trust and they pay security auditors or researchers to write assertions. Because as a dApp, as a protocol engineer, it's very easy to see if an assertion is relevant to me because it just tells me a state that I don't want to. And then that's easy for me to reason about. Is that state that is expressed here wanted or unwanted? Because I posit that all the protocol engineers, they know what they don't want to happen. They know what state their dApp doesn't want to go at, right? They know that their TVL should not fall to zero in one transaction. They know that their smart contract should not be upgraded while they sleep. They know these conditions. What they don't know is that maybe there is a storage variable conflict in their upgradable contracts, or the private key got leaked, or there was a malware on the computer which will be activated like the Radiant protocol hack and will intercept the MetaMask request, right? They don't know the how. That's the complicated part. But if you encode the what, the end result, it doesn't matter how that ended up. It doesn't matter whether it's a code vulnerability, whether it's a bug, whether it's a private key got leaked or whatever. It doesn't matter the how. You cover all the root causes because the assertion doesn't check the path it took. It just checks the end state. So because the assertions are path independent, not only they're easy to write and easy to reason about, but they also cover all the possible paths.
No, absolutely. Yeah, yeah. It's much simpler code for sure. What I really want to talk about with you is what would it take to integrate Phylax into existing layer twos, for example? How hard is it? What would it take?
Yeah, so our first integration will be with the OP stack, right? We're very heavy into development with that. We're in active collaboration with a number of parties. Basically, to integrate with a network, we need, an actor on that network to implement the assertion enforcer spec, right? When they add, as they add transactions, or whether actually we don't need transaction inclusion, we need transaction exclusion rights. So we need an actor. So to be able to do what the assertion enforcer should do is not to be able to add transactions, it's to be able to exclude transactions. So for example, even a relay could do that on the Ethereum PBS spec. So for the OP stack, the way we do it is we're building OP Talos, as we call it, which is a block builder. So we use rollup boost, which allows OP stack rollups to have an external block builder to the sequencer without requiring any change to the sequencer itself. So we're building this, a block builder based on the Flashbots R builder, which will have a vanilla behavior, right? We don't make any MEV. It doesn't make any MEV choices, right? So it has the default behavior, except that it also checks the transactions according to the assertions. So it also, enforces assertions. Oh, I lost you for a bit.
Sorry, man. Yeah, yeah, yeah. I had to open up the door. Sorry. Yeah. Where did we can you repeat like the last 15 seconds? I need to cut this out. Sorry, man.
Yeah. So to integrate with the OP stack, we're building the what we call the OP Talos. So the OP Talos is basically just a block builder built on top of the R builder developed by Flashbots, which also acts as an assertion enforcer. And it integrates with OP stack sequencers via rollup boost, which a software developed by Flashbots, which enables the sequencer to have an external block builder without requiring any changes to the OP stack spec. So this is how we integrate with the block builder with OP stack specifically. But this design is generic, right? The assertion enforcer just needs to be an actor in a network that has exclusion rights to a group of transactions, and then the dApp just needs to trust that actor to send transactions that interact with the dApp, right? in theory and actually in practice, we have designs of how this could work on Ethereum mainnet, for example, where the DApp would say that I only accept transactions from a group of block builders, and these block builders operate as insertion enforcers. Because the design is very generic, it can actually function with any network architecture. We just need to implement the assertion enforcer spec for the appropriate actor, right? And this way, we're also looking into application-specific sequencing, Celestia rollups, etc. The idea is that all of these dApps, no matter on what network they are deployed, they use the same primitives, the same language to express security constraints. So the protocols we just described, the assertion enforcement market and the state oracle and this dApp is deployed on every network to coordinate the actors on that network, the dApps, the assertion enforcers, etc. So we have all these like sovereign deployments of the credible layer, but all of them share the same primitives and the same language, right? So you have this layer on top of all these networks where the dApps use to express their security constraints.
Okay, I see. I would love to talk about a little bit about UX, like or DevX, right? What would it take? Like, I want to write an assertion now for the protocol I wrote. Do I go to your front end, or is it like a Foundry plugin, or
It will be a
how does
foundry.
it work exactly?
It will be basically just a foundry fork with an extra cheat code to execute the assertion. So you can use the same mental models, set up your testing conditions, and test whether an EVM call will be a valid or invalid according to some assertion you wrote. And then with a CLI one-liner, you can submit the assertion for your contract, right? I am and the whole team were obsessed with DevX. We spend an enormous amount of time thinking about that, and this is why both the UX on the dApp and the DevX on the CLI side will be blissful. We see a lot of competitors who they're building very complicated software, very good software, really good tech actually, and useful tech. And it's very good that we have all these competitors because it's not one company that will push the envelope forward. Even though I would love to be in a monopoly, but I really care about the space, and I think it's good that we have so many players. But I think our edge will be on product development and building software that is very simple to use. And if it's simple to use, then everybody will use it. Because security has this very weird thing where everybody talks about it, but everybody thinks they're better than it, and they think that it will never happen to them, right? So why spend a lot of time and resources on something that will never happen to you? So it's not up to us to convince them that they should use our software. It's up to us to lower the activation energy for our software so much that it doesn't make sense not to use it. And I think that's how
So
we,
you're
that's
trying
how
to
we
keep the
win.
developer experience as close as possible as what we already
Yeah.
have, basically.
Yeah. And I think our open
That's
source
awesome.
standards are very important. Like, there is no vendor lock-in in any part of the protocols or tools we make. So the tools we use, open standards, Solidity, Foundry cheat codes, etc. The protocol, you can, register your assertions, and at any point of time, you can just deregister. No hard feelings. And to integrate a network, the network doesn't have to change anything on their protocol stack. They can be superchain compliant and OP stack compliant or Arbitrum compliant, and they can just use our software, as this middleware. And if they want they don't want to use it anymore, they can just remove it and nothing will change on the network. For us, it's very important to have no vendor lock-in, and no vendor lock-in in any way, either through the software, through the registration, through the tools and languages you have to learn and use to use us, right? And that I truly believe that this open source ethos can push security forward, because if I write a good assertion and I share it, then other dApps can adopt it that share design patterns, and I push the security envelope push the envelope for the whole industry, and this is how we win as an industry. Now, security is very walled gardens, and I think that's great for business models, but that's not great for the space. So we want to do things differently.
That's true. Looking into the future a little bit, like how far away are we from like a Phylax, a test network or something?
So we are talking with a few networks already to integrate. I would say we are very close to an internal DevNet, and finalizing the toolchain and the toolchain and the network work, so we can have a DevNet, we can deploy our own assertions, you can compile them. We have a very active community, and we want to leverage that more. And over the next few months, you should be seeing the first networks to launch a DevNet, or maybe to have their test nets be Phylax inside, right? And very soon, hopefully, we can go to production, so that we finally stop hemorrhaging billions of dollars to North Korea. I think an amazing stat is that the Ronin bridge was hacked for $600 million. We know that, and it's also proven that all these funds found their way at the end to addresses associated with Lazarus Group and North Korea. We know that. That's proven. There is open source resources to find that. We also know by approximation that their nuclear program is around $1.2 billion, give or take. So the Ronin hack financed half their nuclear program, right? So it's an amazing stat. Can you see me? I'll ask
Amazing.
you for a bit.
Yeah.
Yeah.
I can.
So
The Ronin hack financed half of the nuclear program of North Korea.
yeah. And it's time to
Fantastic.
put them out of business, right? It's time to put Group Lazarus out of business.
No, it's true, man. Listen, it's like even for someone like me, if you write smart contracts, you know the risks. Uh, so it's hard for me personally, for example, to deploy capital into something where it's like a 1% chance of losing everything, for like 8% yield. It just doesn't make any sense.
Yeah, exactly.
It's just the truth. So yeah, no, that's it's super important. Obviously, I'm rooting for you guys. It's a cool project. Would love to see a DevNet. Write some assertions.
Soon.
That you said docs are coming soon. Open source code is coming soon as well, right?
Yes. Yeah, exactly.
Awesome. Yeah, then I think we're nearly at 1 hour. This was a pleasure.
It was a pleasure as well.
I'm
Thank you
gonna
so much.
Yeah, man. This was super interesting. I'm gonna put the website, the Twitter in the bio down below. Once there are docs and code, I will put them there as well. I think your guys are hiring as well, right?
Yes. Yeah. Yeah. We have 2 active positions open for a front-end engineer and a Rust engineer. Yeah. So if anyone is interested, we would love to talk to them and we're looking for people that want to hustle and they want to tackle very big and important problem. Right on, right. because we think that what we're doing is extremely important.
For sure, for sure. So yeah, if you know your Rust and your React, you want to work on something interesting, reach out to Odysseus and the Phylax team. Odysseus, again, thank you very much, man.
Thank you so much, man. Have a good one.
Awesome, guys. Yeah, see you in the next one, guys. Bye bye. Take care.